everyone. Today we will be taking up Module 3. Please go to page 14 of your notes. In this module, we will explore the information given by the periodic table that goes beyond being able to determine electronic configuration. You may think that an element is much like an onion with layers or shells of electrons over top of each other that expand further and further out from the nucleus as we go down the periodic table. So let's review a few definitions. When looking at a particular element in the periodic table, its core electrons are those in the inner shells closest to the nucleus, and we have defined them by the closest noble gas written in brackets when we wrote configurations. These electrons are buried and unreactive. They will not form bonds. Then we have the valence electrons. Those are the outer electrons in the most outer shell. Recall that those are also the electrons of higher energy. These are the electrons that will be reactive and will be involved in making bonds. These electrons are contained in what we will now call the valence shells. Thus, you should now realize that the orbitals involved in the valence shells will be involved in the bonding process. Taking carbon as an example, its configuration is helium in brackets, the core electrons, 2s2, 2p2. It has 4 valence electrons. Looking at iron, atomic number 26, the core electrons are defined by argon in brackets, and the valence shells involved in bonding are the 3d and 4s orbital. 3d contains 6 valence electrons, 4s contains 2 valence electrons. Let's talk here about the magnetic properties of elements. Recall that an electron is not static, it spins. In doing so, it generates a tiny magnetic field. So really, it behaves as a small magnet that has a small magnetic moment. Recall as well that we give electrons spin numbers and that an orbital can contain up to 2 electrons, but they have opposite spin numbers. In other words, the 2 electrons spin in opposite directions. Thus, the small magnetic fields that each electron generates, it's in that same orbital, actually cancel each other. Expanding that to the property of elements, we have elements that are called diamagnetic. This is the diamagnetism. Those elements are not attracted or slightly repelled by external magnetic fields because all of their electrons are paired. We will also have elements that are paramagnetic. These are the elements that have unpaired electrons. Therefore, they have a net magnetic moment that is the sum of all the small magnetic moments generated by each unpaired electron. So a larger number of unpaired electrons will generate a larger magnetic moment. These elements will be attracted by magnetic fields. Let us look now at the periodic table and define periodic trends. Beginning with the size of elements, that we can define as their atomic radius. The atomic radius decreases from left to right on the periodic table. Elements in the same period have the same principal or valence shell, but as we go to the left, the number of protons in the nucleus increases concurrently with the number of electrons. That results in a stronger attraction of these electrons by the nucleus and a decrease in the size of the element. In contrast, looking at elements in the same column, going down the periodic table, the size increases as we have more shells of layers of electrons, kind of like the onion. So the atom, as we go down the periodic table, get fatter and flabbier. How about the ionization energy for each element? This is the energy that it takes to remove the electron of highest energy from the element. Recall that full electronic configuration, such as that of the noble gases, is stabilizing. So it should not be surprising to you that those are the most stable elements that have the highest ionization energy. It should also make sense to you that alkali metals, group 1A, have the lowest ionization energies, since removing one electron leaves them with the electronic configuration of the noble gas from the previous period. In general, ionization energy increases from left to right in the periodic table. As we are talking about the same principal shell, since the nuclear charge increases, electrons become held more tightly. Note that there are anomalies. Every time we change from S to P, it is easier to remove the single electron in a p orbital than it is to remove an electron from the full s orbital in the previous element. So compare, for instance, beryllium and boron. It is also easier to remove a single paired electrons in the 2p oxygen or the 2p orbital of oxygen here than it is to remove an electron from the half-full 2p orbitals of nitrogen. Looking at the periodic table, top to bottom, the ionization energy decreases as the electrons get further and further away from the positively charged nucleus. So therefore, they become easier to remove. Electron affinity is the energy that is released when the element gains one electron. You can think about it as how much does an element want an extra electron. It is linked to how much stability would one extra electron bring to the element. As you can see, electron affinity is greater for those elements closest to the noble gases. In fact, it is highest for the halogens, here group 7A, since having one extra electron gives them the configuration of a noble gas. Now that we have talked about ionization energy, giving us cations, and electron affinity, giving us anions, let's talk about the relative sizes of ions and neutral elements. First, removal of an electron will result in the ion being smaller than the parent element. So sodium plus here is smaller than sodium. This is because the electrons are now held more tightly by the nucleus. In contrast, addition of an electron results in a larger anion than the parent element. So chloride here is larger than chlorine because the electrons are not held as tightly. Finally, let us talk about isoelectronic series. These isoelectronic series mean that all the ions and element in the series have the same electronic configuration. So for instance, here, all the ions, O2 minus, F minus, sodium plus, magnesium 2 plus, aluminium 3 plus, have the electronic configuration of the noble gas neon. In this series, the radius varies directly with the charge of the atom. So the largest negative charge will be the larger ion, then will come the fluoride, -1, then the neutral element, then sodium plus, only one positive charge, then magnesium 2 plus, then aluminum 3 plus. So one last periodic trend, electronegativity. It is defined by the Linus-Pauling scale. It tells us which way the electrons are lying in a covalent bond. In other words, it tells us the ability for an element to pull the electrons in the covalent bond towards itself. Think a covalent bond as an orbital shared between two elements. When one of these elements is more electronegative than the other, the cloud of electrons is distorted towards the more electronegative element. Remember, forever, fluorine is the most electronegative element of the periodic table. And the second one is oxygen. In general, electronegativity increases from left to right in the periodic table and decreases from top to bottom. So students, this concludes our first chapter on atomic structure. Now go to activity number 3. Bye for now.